Thanks for coming. We're going to speak about applied explainability. TensorLeap is explainability and debugging platform for neural networks. We're experts in explainability that dedicated for development processes. We're trying to establish a new term. We're trying to say that if we'll invest enough time and effort to explain neural network, we'll be able to utilize the insights of those algorithms in order to automate a lot of processes in the development cycle. We're saying that if we'll manage to explain those models and to understand the different features they manage to learn, we'll be able to understand which data we can label, which data we need to construct, where we might fail, and to accelerate the fixings of failures in production. So let's first of all maybe summarize and understand the status of the current development paradigm, right? We're handling with a huge data sets because we're just constantly collecting random samples. We don't know which samples we need. We don't know which information they contain. We have this first assumption that as much data you have, you'll get to better performance. We're splitting training and validation. Most use cases randomly. Sometimes you have times that you can use and take until Thursday to training and Friday, Saturday for testing. But what does it mean? Does it will give you the confidence that your model managed to generalize information? We have many unrepresented population from the very same reason. We don't know which feature defining those populations, so it's going to be very, very hard to understand all the different scenarios and to make sure that this information is balanced correctly. And all the tagging and labeling procedures, every time we'll say, okay, we'll ask the tagging teams set when that the image contains cars and when it's took from the morning, and then maybe later I'll be able to distribute the model performance on different scenarios, but still those tags are biased to our own perception, like it's how we see the data. And this conformational bias, it's a huge issue. Our testing procedures are a nightmare. No ones that achieve 98% accuracy on this model will feel comfortable to let it drive autonomous vehicle, right? We constantly have 500,000 samples, and we'll have that will achieve constantly this 98% accuracy. Every model you produce this week, but each one of them tending to fail on small population. Those small population gonna represent a really very real scenario in production that this car gonna make a severe accident. And the main problem is that they're constructed from too small populations that will never move this 98% accuracy on the total data set. Our testing techniques are not implied for generalization. Accuracy, it's not a generalization metrics, right? You will never know if you won't measure the model ability to generalize information, the features that it used, how generalized they are. You won't understand if you overfitted to your small subset of the real world, right? And even if you manage to fix some problem in production, again and again, and you have hundreds of problems in production that you manage to fix, we don't have any mechanism today that makes sure that you won't fail on those failures tomorrow with the new model that you'll deploy. Last subject, troubleshooting. When we're failing, it takes us way too long to fix. Because the current paradigm is to look on the samples, say, all right, this very bright edge maybe will confuse my model, get into trial and error experiments. Maybe one of them will fix it, and it's going to take time. We're going to have it's going to be very hard to explain our clients why we're failing, because we're guessing why we're failing. And it's a huge problem that we cannot estimate the severity of those failures, where the model going to fail again from the very same reason, right? So applied explainability. Applied explainability is a set of tools that can take all information within the model, summarize it, distill it to a human language that we can utilize and understand those different phenomena and information the model managed to learn. And the idea is to be able to take all this very complex interface and to utilize it within the development process itself, to build those tests, to cure your data set, and to handle failings in productions. The first thing, I'm gonna run on it very fast because it's gonna be a bit complicated and people need food. So we're gonna track after all the activation within the neural network. We're gonna measure a lot of indicators like entropy and mutual information between different activation to the prediction, between the different activation to different scenarios and different metadata in your data set. We're gonna track after all the gradient, and we're gonna collect a lot of information per each one of those neurons in order to understand which one of them learned some significant information, which one of them managed to distribute reality well. And after that, we'll create a different pipeline that will distill this latent space in order to be able to represent millions of samples. From there, we'll conduct clustering. We'll find all the population that we can define with the features that your own model learned, and we start to characterize them. We will search for the cluster that are tending to fail. We search for the cluster that the mutual information with the input to those to the most expressed features in those clusters are very high, which is a great indicator for overfitting. And we'll search population that underrepresented in your training set. And the idea to expose it and to be able to explain those different phenomena. So if we track after, if we have a clustering algorithm and we'll extract the feature importance of this clustering algorithm, it will lead us to the neurons themselves that were sensitive to certain information. By tracing back the activation, we'll be able to generate some heat maps that will show us where the information were constructed. So, or we can create different derivatives from different neurons to understand what in the data in each one and one of the sample caused those cluster to emerge or to model to make certain predictions. Now, usually we have a demo. It's a bit, we don't have long enough cable. So if you want to see a demo, you can come to our booth. I'm going to illustrate it with words. So the way we work, we uploading the model, we parsing, we constructing this computational graph, we tracking after all those activation. And the first idea is to be able to take the data set and find all the population that tending to fail in the test set and check if they're represented in the training set enough. And by running the same clustering algorithm on unlabeled data, we can prioritize those samples better. We can find where we have way too repetitive information and recommend which samples to remove from the data set. We can reconstruct the old data set information with unsupervised techniques that rely on the model understanding itself. We can do it every epoch again and again and cure your data set while the model training is progress. Which gonna save enormous amount of time on labeling, right? Because we constantly tagging and labeling and annotating samples that we do not need, and we know it. We'll be able to take problems in production, explain it completely, and instead of guessing why the model failed, we can take the loss function on those samples, derivative it to the most informative information features in the sample, understand which first features cause the model to take a certain prediction, trace back to activation, generate failures, take some projection of this latent space that capture the essence in the failures in these samples, and query all production to find where you're gonna fail from the very same reason, and estimate the severity and explain why it caused, and then to conduct much more focused experiments that check it. And after we fix the issue, we can explain the prediction and see that we didn't overfit it to certain information that were part of this small subset that we used. And the main, and maybe the most important part, is to be able to take this test set and to split it to thousands of small population sets and to be able to track after them. So what we are doing, we're building a huge databases in the background, the tracking after the performance indicator of each sample, together with all the features that learn the important information in these samples. And we're labeling and indexing it, all information in huge databases. And then every model that you'll import to the system, we constantly search on which population it might fail that where the previous model didn't fail. And we'll be able also to tell you, it's not that you got to 98.5 accuracy result now, and before you managed to get to only 0.2. This new model perform much better on 50 new small populations. And those are the population. And this is the information that it learned. And the ability to generalize improve times more than the previous one. We can get a real confidence in the model that we are deploying. Question, guys? Some of them, you can rely and use different kind of backpropagation techniques in order to understand in which information certain neuron predicted, the way it predicted, from which area in the image it happened. But when you're trying to search, for example, all the similar cases that the model behaving from the same way, you'll use a bit different techniques. You'll distill the latent space, features from different layer. You'll project it on certain loss function that's symbolizing the failure in this use case, and you'll apply some similarity cosine search to find the samples that failing and that representing with the same features. And we're speaking about a huge set of tools that combine together into a product that will allow you to utilize it within the development process. But some of them are very similar to backpropagation. Yeah?
Between the overfitting cases and actually strong features.
Again? Sorry.
Overfitting in the latent space and the strong features.
Overfitting in the latent space and the strong features. Yeah. And what is the question?
How do you distinguish between them?
How do we distinguish between them? All right. So it's a great question. And overfitting, it's a matter of maybe perspective, and everything is relative, especially information. So we have different techniques, and we not claim to automate the whole development process. We need man in the loop. We need a data scientist to look on our insights and decide if they are still validating, if you want to do something with it. So, for example, the indicators that today we use in order to detect those overfitting, of course, we have a bit more resolution and a bit more ability to automate and to run on millions of samples. So we'll be able to detect clusters that just tending to fail more on validation than in training set. Simply. But we'll also track after the most expressed features that in each cluster, and we'll measure the mutual information between the rest of the populations. So if you have certain features that define perfectly certain cluster, and they expressed only in this cluster is not sharing this information with other cluster. This is the definition of generality. If you want to generalize, you need to share the information with more samples. So we're measuring mutual information of the most expressed features with certain cluster, those that we claim that they overfitted with the rest of the data set. And we also have respect to the depth of those features. So if those features are very deep in the system, they are very semantic, they should be more common among different clusters. If they aren't, we're using different techniques to detect when it's too deep and too specific to define one cluster. And then we can utilize it in order to claim and to explain overfitting. Cool? Yeah.
Last question.
A quick question. I was just wondering, you're using the explainability techniques for debugging the models. Mm-hmm. Do you see already applications, and of course the human in a loop, I just presented about it, where you are using the learnings of a human by the debugging techniques to improve model?
We definitely have a human in the loop, and this feedback to the system is super important. Part of the most important integration is to allow the client itself to explain the insights you see. So we constantly will take all the metadata the client provided us, and while we floating up those insights, we'll tell them to which metadata it's correlated in order to be able to describe the failures and the model behaviors with the client language itself, right? Which is very important. And also there is kind of feedback that when you found a certain dimension that can distribute the data set in an informative way and can imply on scenarios that you're going to fail on, it's very important to be able to describe it with a deterministic models. Because everything that we'll do unsupervised will never be deterministic, and it won't define reality good enough, in a concise way that you can repeat and make sure that. So it's very important to combine this man-in-the-loop with deterministic techniques to define and explain those systems.
Yeah. So I was wondering what exactly is the output of the product. For example, I supply a deep learning model. It does segmentation, my model, right?
Yeah.
And then you basically connect to that model, and then you supply some kind of output where you identify issues. So what exactly do you supply? And then how I'm basically supposed to use it?
Yeah. So those are images from within the system itself. So the first thing you'll do is to upload your model. ONX, H5, protobuf, any kind of format that can represent the structure and the weights. We reconstructing those models to our own language. We translating it to some TensorLeap language, and just to be able to add all the mathematical operation on each activation that we need to start to track and measure. The first thing you'll get is some similarity space that shows the different similarities between samples, with heat map that shows what is the main features that expressed in them. And on top of those similarity space, we'll provide all the metadata and performance indicator that can show us which cluster tending to fail more. And then you'll just get a list of, we don't have the image here, but you'll get a list of insights that tells you we found 500 samples that define with a very specific information that we extract within the model itself. It correlated to images that took in 12 in the noon, red cars, and different metadata that you can provide. The model tending to fail there 30% more than the average. And here is a clustering algorithm that's sensitive to this information. And with a click, you can connect us to unlabeled data, and we'll scan this unlabeled data and return to you with another analysis that shows you which samples you need to add to the training set in order to solve it. With explainability techniques that will show you for each unlabeled data, unlabeled samples, what is the information within that image that contain the information that you need to add to the training set in order to solve those problems. And the other side, we have a list of dashboard that we take in all those information we process and we indexed, and allow you to distribute the model performance on different dimensions, and to choose the small subset of scenarios, of edge cases that you want to start to track after, and we'll get a screen that looks like that tracking after the performance of each one of them. Now, it's very important to understand TensorLeap is not a Python library. It's a big system. It's full of 4 or 5 different databases. Each one of them is vector databases for the embedding, and big data databases to index millions of performance indicators on all your data set in each epoch. And we have a lot of infrastructure with a lot of small microservices that are in charge on the gradients and in charge on extracting the indicators per activation. So what I'm trying to say that when you add a new model and you want to see on which population it tends to fail, you won't need to reevaluate this model again. We're indexing all the information ahead. We're tracking after all the activation ahead. So you're just uploading a model once, clicking a button, and we applying all the techniques before, and then you can just track after. The main idea is to be able, if we're asking about what you gain out of it, except of the platform itself, the main idea is to allow you to connect it to data pipeline management platform and CI/CD in order to conduct the test properly, to understand when you need to deploy a new model and in order to reconstruct the data set that you're using for training.
Is there original research in this system, and if yes, have you published it? Thank you.
Yeah, so we are a startup. We are running fast. We wrote a lot of content. We'll publish it more soon. None of it, we haven't yet invested the effort to publish scientific research. But blog post, we're trying to share as much as we can to gain more trust. We'd love to jump into Zoom meeting with anyone and get into the details of what we are doing and how we are doing and everything. We have a great, very strong mathematician team that building all those tools. So we'll share more soon. We're just young yet.
Right. I think that's it. Thanks very much, Yotam.